So welcome back, everybody. And the topic today is just a continuation of where we landed last week. So we are dealing with these methods about linear regression, which deal with linear regression. And we labeled them last week as a kind of low-level type of machine learning. And this method allows us to bring in many of the basic concepts. We can calculate analytically the expression for the parameters. We can find analytical expressions for the expectation values, the variance, etc., etc. So there are many benefits in dealing with linear regression. And we can also link this linear algebra-based approach, which we looked at last week, with a statistical interpretation. And we are coming back to that. So it's a kind of way to introduce many of the central key aspects. And for those of you online, the basic link to everything is given in the GitHub address here. And you will find then tentative descriptions of the first projects. Many of you have already come with feedback of what you would like to do. So there are many different paths, but I think we can make something which triggers everybody in one way or the other. And then when we come to the third project, like last year, we actually had many different paths, which more aligned with people's research projects. Now, many of you have not had much machine learning, but you've been doing computational science in one way or the other. So if some of you find this too elementary, I mean, you can just try to digress into something else if you wish. Typically, what you will find is if you scroll down here on this main GitHub address site, you will find the slides which we're going to cover on a weekly basis. And you will also find the video of the lecture after the lectures. And similarly, you will find the handwritten notes. And last week, one of the things we did was also to discuss how to calculate derivatives of matrices and vectors in terms of vectors and matrices. And this is very handy when we want to calculate the gradients of what we call the cost function or the loss function. So the topic today is something which deals more with the methods which you can see as an extension of ordinary least squares. And one of these methods, reach, was actually introduced as a cheap trick to avoid a divergence or a determinant or a matrix which is not important. And what we will see later is that we can make a nice statistical interpretation of ridge regression as well as Lasso regression. Ridge regression is a method which also gives us analytical expressions for expectation values for the parameters beta of the model which we have chosen, and so on and so on. But please feel free to interrupt me and ask questions if something is unclear. So if you dive into the topic for this week, we are going to look at mainly at the Lasso ridge regression. The lecture, the video will be added. But before we actually discuss many of these topics, I wanted to bring up a topic which is sometimes something which causes confusion for people. And that is about scaling of the data and why we typically scale data. So one thing which I will not put so much emphasis on in the lectures is actually the preparation of the data. So in many of the examples which I'm going to run, we are going to have normally what we call a vanilla type of data. So that's a simple polynomial. I can just generate as much data as I want. But in real situations, often you end up spending 80–90% of your time in tailoring the data and preparing the input for a machine learning algorithm. And that's really the kind of painful thing. And one of the things which we typically are going to deal with in this course is more assuming that you have the data. We still need to do some extra massage of the data, in the sense that we want to get rid of the possibilities of training with outliers. We want to scale them to a smaller region. just to give us, you can see an example here. If you have a data set with health habits, it may contain age, which spans many, many years, caloric intake, or we had an example of a student who did a master thesis on predictions of wind directions based on meteorological data. And we spent something like 2 months and we couldn't understand actually what was going on. And the problem was that the wind was measured in different time periods, and in some periods it was registered in terms of meters per second. In other years it was registered as a kilometer per hour, and some of the data came with miles per hour. And we didn't realize that before we actually looked more deeply into the data set. And some of the data may actually be punched in wrongly. So typically you can have an output of the type false true, which you would label with zeros and ones, which is a very common case. And sometimes humans punch in 2 instead of 1, right? And you can see that. So to traverse the data set is actually something which is very important. Look at the data. And one of the things which we then need to think of are different ways to actually scale the data. Sometimes it's convenient if you have data which go from a -1 million to plus 10 millions, you could scale the data between 0 and 1, just to give you an example. And that can sometimes make it easier for the numerical algorithms. Because remember from last week, when we looked at the parameters beta, we were actually setting up the inversion of a matrix to find these parameters. So let me, before we now look at the scaling in more detail, let me quickly remind you of what we did last week. So let's just spend some few minutes on a quick reminder. And I'm just going to switch to the whiteboard here. Sometimes there's a delay here to bring it up. So what we did last week, we defined our data set. So we had a domain of data, and that contained what we label as the inputs, and then we have the outputs, y. So these inputs could be a vector, or they could just be a scalar. And then we have the specific outputs, which could be, let's say, the wind speed. It could be a classification case where it's true or false. That means 0 and 1, and so forth and so forth. So we had y1, and this went all the way up to the final point. And since we are going to use Python in programming, I'm going to begin already with this Python-like indexing. And what we did, so this is the data which we had. That was the first point. Then we made a model. And in that model, we assumed that the function we want to set up is something which has a linear dependence on the unknown parameters of the model. And we define that in terms of a matrix X, which we call the design matrix. And so the beta are the parameters, or the estimators of the model. So these are the model parameters, and we call this linear regression because the function which we are picking is linear in the unknown parameters beta. It's as simple as that. So these are the model parameters. Now, this quantity here is something which we call the design matrix or the feature matrix. And just to give you an example, what we have then is a model y of I tilde, which could be given by a polynomial. So this was the example which we looked at last week. So we made a sum over the polynomial degrees. So we have a polynomial, if we have the p points, for instance, we can fit a polynomial of degree p minus 1. P could be equal to the number of points you have. So the data points which we have are n. These are the entries and the outputs. But you can obviously fit a polynomial of lower degree. So you could have a data set with thousands of points, which is given by a second order polynomial. If you're tempted to, you could fit a 999th order polynomial instead of a second order polynomial. So this P doesn't need to be equal to n. And then what we had was a linear expansion in the parameters of beta j. And then we have this x of I to the power of j. So as a polynomial fit, this would simply be given by the intercept, the first point. So I'm just repeating what we looked at last time. This would be xi to the power of 1 plus beta 2 of xi to the power of 2, etc., etc. Till we move up to the final parameter of xi to the power of p minus 1. So this is the model which we are making. And then one of the assumptions which are made here, when we look at linear regression, so you could think of this as a kind of overarching model assumption. So you have an assumption where your y of x of I, which is given by y of I, like this is given by some deterministic function plus some normally distributed noise. So we can just rewrite this as an f of I plus epsilon I. And this is a normally distributed noise, so we normally write it like n, or normally distributed, with 0 mean value and a variance sigma squared. And then this quantity here is assumed to be a continuous deterministic function. That means that there is no stochasticity in that function. So later you can actually change this. But in standard linear regression, this is one of the basic assumptions. So this is a deterministic function. And in a certain sense, it fits well if you're looking at many of the settings which you can end up looking at. Suppose you're running an experiment and you have you're preparing a beam of particles. That is something which could be well described. If the beam is well focused, then you know exactly what the frequencies of the incoming particles are. So that would be an example of something which enters this deterministic function. And then you have some output due to the incoming beam. So the x's are fixed, well determined. And then you have some noise which you add to the kind of overarching model. And then you proceed with that assumption. So this is an assumption, and what we have done is actually to take this y of I tilde, and we have made an approximation to the function f of I. So this is what we did last week. And with that assumption, we define then a function to assess the quality of the model. So this is the assessment. Assess quality of model. And that leads to the definition of what's normally called the cost function or the loss function. Some people call this the cost, like this, loss. Some people call this the error function. Some people call it the risk function if you're in finance, etc., etc. And I'm just writing this as a function. And in our case, we define this function to be a function of the parameters beta. And what we did was to use the mean squared error. And that became 1 divided by n. And then we have a sum over all the data points we have. And we have y of I minus the model we have made squared. And this is something which is very sensitive to potential outliers. So it actually magnifies the possible outliers. Now, this is the same, and we wrote this in different ways last time. We could then rewrite this as an I equal to 0 to n. I'm just repeating what we did last time. I hope I'm not boring you too much. J equals 0 to p minus 1. And now I'm just setting up these parameters xij, which could be the parameters of a polynomial fit. So this would be our x's to the power of j, or it could be some other function which we have opted for. And this was given by the parameters beta j squared. And we can rewrite this in terms of 1 over n we can take the vector y minus this matrix X, multiply with beta, transpose, and y minus X times beta. You will also see this written out as a norm 2 minus X times beta. So this is the norm 2 of a vector square. So y is a vector. Let me just quickly remind you of these quantities. So X is a matrix, which now contains these different matrix elements. So if you have a polynomial fit, the first column would be the intercept column, corresponding to this beta 0. And then there's x0 up to x0 p minus 1. And then we have x10 down to xn minus 10. And this goes all the way up to xn minus 1 or x p minus 1. Now, in the case which we have been looking at, so X is a matrix of dimensionality n times p. So I'm going to use that way to sort the input variables. So that means that the rows correspond to the entries which we have, the data inputs, and the columns correspond to given features. In our case, the given features is a polynomial order. But the feature here could be, if we're looking at a data set we are going to encounter later, there's a famous data set which is called the Wisconsin breast cancer data. Then every column will represent a feature of a given tumor. And that could be the radius of the tumor, could be the thickness, it could be the surface, etc., etc., etc. And these are features which a pathologist uses to assess whether this is a benign or malignant tumor. So this matrix is normally called the feature matrix or the design matrix. In our case, X, this matrix X, is given by 1 because these are just the intercept. This is the intercept column. The next one is x0, x1, x2, down all the way to xn minus 1. And then we have x0 to the power of 2. And this continues all the way to x0 p minus 1. And this goes all the way down to xn minus 1 to the power of p minus 1. So this is the specific case which we looked at now when we are fitting a polynomial. But you are not limited to polynomial. These x's represent a sine function, it will represent a cosine function, or more complicated functions. Okay, any questions so far? So it takes some time to adjust to this kind of way of thinking. So what we're doing now is that we are representing the input data in forms of a matrix. Clearly, if you have only one variable you're feeding in, let's say x, then you just need a column, right? So if we are now thinking, if we go back to what we have up here with the domain of data, if x is just a scalar, then we would just have one column which defines the design matrix. The next thing which we did last time was actually to find the optimal parameters. So what we have done now is to find a function which we use to gauge whether the model is a good one or bad one. And then we want to minimize this quantity. And that leads in general to a convex optimization problem. So one of the things which we did, basically where we landed last week, was then to take the derivative of this function, c of beta, of the unknown parameters of beta, and we want to put that one equal to 0. So essentially what we are saying now is that the beta optimal, so these are those which give us the smallest mean square error. So when I put this hat on it, it's just an optimal quantity, optimal beta, is now given simply by the minimization for all betas, and we have p of them, of this function c of beta. And the way we do that is to calculate the beta. And when we did that, what we found is that this gives us a parameter beta at the optimal ones, which are now given by the inversion of this matrix, times the transpose of the matrix times 1. And when you look at the dimensionalities, you see immediately that the dimensionalities fit and that they're okay. So data has length p, and when you now set up the quantities here, you see that the matrix which you have to invert here, this is a matrix which has dimensionality p times p. And in general, for many of these methods, p is smaller than n, the total number of data entries we have. And actually, the more general case is that p is much, much smaller than n. So if you have 10,000 patients and you've been scanning through the different tumors, you may have 30 features. So that means that 30 is much, much smaller than 10,000. And the matrix here is normally a small matrix. Now, you can quickly see that the methods we are going to discuss, you run into problems if you want to do genetics and look at which parts of the DNA are responsible for this and this type of tumor. Just to give an example. In that case, you can have zillions of combinations, so tons of features. You can easily have 500,000 or more features, and clearly then these type of methods, they will break down. So the typical situation where you would use this type of methods are the cases when you can invert the matrix, or with some method, which we are coming back to, and where the dimensionality is not too much. Another thing which we found last week, actually did that as a kind of small exercise. If you take the second derivative with respect to beta and beta transpose, this is now given by 2 divided by n, and it has this matrix X transpose times X. This is something which we will show later is going to give us a convex problem. So it means that the eigenvalues of this matrix are semi-positive definite. And that leads to a convex optimization problem. And this is something which is, from the point of view of linear regression, is a very benign type of problem. So when we deal with deep learning and neural networks, we have no idea whether this is a convex optimization problem or a concave optimization problem, or whether there is a global minimum or a minimum. So this is a clear case. So just keep that in mind. We're going to show that this is going to be a semi-positive definite matrix, which means that all eigenvalues are larger or equal than 0. And that leads to a convex optimization. So that's very important. So we know that there is a global minimum. Okay, any questions? So these are just technicalities. Now, if we know what we're going to do now is just to look at some very simple examples. And we're going to look at a technicality which is a little bit, I would say, it doesn't sound that exciting, but it can be important. And that deals with scaling the data. And what I'm going to talk about now is particularly important if you're doing a polynomial fit. The reason for that is that, so let me just write this. So this leads to a convex optimization problem, which means again that we have a global minimum. There is a minimum. So there is a minimum, which actually, where we have a minimum value for this cost function in terms of the parameters data. Now, I also want to anticipate some of the things we will be discussing a little bit later. And we mentioned that last week, that so we have these 3 basic elements. We have the cost function, or risk or loss function. So normally many people actually call the sum of the individual contributions of the loss function. But now there's a kind of general jargon that the cost function is also called the loss function. You can go to other fields, you will find it as a risk function. But this is a quantity which we use to assess the quality of the model. It doesn't need to be the mean square error. It can be other functions. Then we have the model which we are making up, and finally we have the data. And at the end, we end up with an optimization problem because we want to find the optimal parameters which minimize this cost function. So this leads to the topic of optimization problems and convex optimization problem. And this will also allow us to bring in some linear algebra, which deals with the gradient descent methods. And some of you may have heard about steepest descent, conjugate gradient descent. And there's a whole theme in machine learning which deals with optimizing these gradients. This will also lead us into automatic differentiation. And this is a very powerful algorithm where you, by the chain rule, can calculate derivatives to numerical position. So there are some interesting topics which allow us to link with algorithms from computational science, which are extremely useful. So I know that some of you have heard about the backpropagation algorithm. And in automatic differentiations, there are two modes, forward mode and the reverse mode. And the reverse mode is actually the backpropagation algorithm in the deep learning methods. So we are going to discuss these things a little bit later, because if you really want to nail down the bottleneck in all machine learning methods, the bottleneck is actually here. And calculate these gradients. So it doesn't sound like an exciting topic, but as I mentioned last week, this is the place where you can get many, many more friends. And I don't infer that you don't have friends. Does not mean that. But it will be friendly inside you. And there are algorithms like ADAM, which is an adaptive momentum-based method, which came out in 2014 as a paper which is not even published in traditional scientific journals, and it has 120,000 citations. So these are, if you really can make some advances here and speed up the optimization problem and the calculation of gradients, this is something which is extremely valuable. Now, one of the things which we are going to look at now is this strange topic of scaling of the data. So this is a technicality. And one of the reasons why we scale data is, one, we would like perhaps to have the data in dimensionless units. That's one possibility. And perhaps we would like to squeeze it down in a smaller domain. So if the data vary a lot, you can make a transformation to a smaller span of values. And one of the reasons for that is that if you look at the problem which we have here, either here or in the calculations of gradients, one of the problems we face is that if we have a huge span of values, we may actually run into problems like loss of precision and loss of numerical precision. So that's why we often try to scale the data to a smaller domain in order to avoid potential numerical errors. So even if we could calculate easily the determinant and the inverse of a matrix, if we have a wide range of values, then that can lead to problems like loss of numerical precision. Or you can get overflow or underflow, which are also unwanted features. Just to quickly remind you, if you think of underflow, that means that there is a smallest number the machine can represent. Similarly, you have overflow, which is the largest number which can be represented. So if you're dealing with double precision numbers, the largest number is typically 10 to the power of 308. So if you go beyond that, then if you haven't put flags, the compiler will keep running, or the program will keep running, but it puts all values to 0. So a typical example is a calculation of factorials. Factorials, I mean, I'm preaching this now, but I made this stupid error so many times. I actually had a problem on harmonic oscillator functions, which is a ratio between two factorials. And everything was running fine when I had small factorials, and then suddenly I needed to go to larger values, like the factorial of 300, and ratio of 300 and 200. So I just got out. And I had simply forgotten everything I preached, that you have a limited number of numbers you can represent them. So if you have a wide ranging span of variables, you can end up in problems like that. So the program will keep running, but it will simply put values of 0. So that's something unwanted. And that's why one of the reasons why we will deal with scaling of the data. So a very standard one is to actually subtract the mean value for every column in the design matrix. And we are just going to look at that one first. You can have other cases where you just map the data for a domain, let's say X, it goes from, as I said, -1 million to 10 billions, and you just map it to 0 and 1 as an example. But let's look at the scaling where we now subtract the mean value of each element in the design matrix. Scaling of this now of design matrix by subtracting the mean value of each column. So let's now look at the explicit case of the polynomial fit. Polynomial fit case. And in that case, what we have is a design matrix, which looks like this. So we have 1, this is the intercept, 1 here. So we have x0, x1, down to xn minus 1, and all the way to n minus 1 to the power of p minus 1. This goes to x0 to the power of p minus 1. What we could do now is simply to rewrite this in terms of 1 here. And then we have the x. I'm just writing it like this. So x is a vector now, which contains, so let me just define that. X transpose is a vector which contains x0, x1, up to xn minus 1. So that means that here I have the x to the power of 2, etc., to x to the power of p minus 1 here. So these are now the column vectors. And I just put this kind of strange labeling on them. I should put this one like this. With different column vectors. Now, what you will do then is to define the meaning for each of these. It will now be mu of this quantity I, so that will be the given column vector, and that would simply be given by 1 over n, and then I have a sum over j equal 0 to n minus 1, and then I have my x of the specific column vector which I have here. So this will be the column vector I, but now I'm summing over the different elements j here. So I'm just simply running over all the elements of that specific column vector, and then I'm calculating the mean value. So in principle, this is just the same as 1 over n. If we are not looking at the special case we have, it will simply be given by xij. Actually, it's the opposite. It's the because these are the column elements, so this should be j. Sorry. So these are the mean values, and that means that we would then redefine this different matrix elements by subtracting the mean values. You see now one thing is that if I do that subtraction with the mean for the first column, what will I get then? 0. Because the mean value is 1, and then I take 1 minus 1 for every single element, and then I just get 0. So you can see there's a potential problem here if I scale. And the reason I'm bringing this up, this applies particularly to polynomial fitting. If you use a popular library like scikit-learn, what that typically does, if you don't put in a flag, it computes the mean value and subtracts one automatically. And then if you use that one, you may run into problems when you're comparing your code with a given library. What is common to do in many of these algorithms, like here, is that you take away this intercept column. So a library like scikit-learn, if you have zeros, then it will simply take it out. So it takes out that specific column which represents the intercept. So let me try to look at the Jupyter notebook before we go through these things in more detail. So this is something you can fit without the intercept. And when you do a polynomial fit, you can add the intercept back in. And you can express the intercept simply by a mathematical formula which relates these mean values and the mean value of the outputs. So let's just take a quick look at that. So this is meant as a kind of small digression, which is also important when we now are looking at some of the fitting here. So what is follows here is just a kind of functionality you will see in, for instance, a library like scikit-learn. So my advice also is that when you're using or writing your own code, use the functionality which you have in libraries like scikit-learn. Scikit-learn is a much used library, and it interfaces with other libraries like TensorFlow and Python. So the functionality you see here, like this scaling your data, splitting your data in training and test and so on, you can use these functions together with other libraries. And there is no deep insight in writing a code which scales the data. If you've done it once, you've done it once, and you don't get any deeper insight if you rewrite for a new case. So scikit-learn has several ways of doing it. One is the standard scaler, which it does by default. If you don't tell it, it actually does the scaling, and it subtracts the mean value for each column in your design matrix. So if you're running your code and you're comparing with scikit-learn and you don't agree, that's simply because scikit-learn has done the scaling without telling you. So you can actually have an option which is called fit intercept, and you would think that fit intercept is equal true is the case when you keep the intercept. It's actually the opposite. So you have to put fit intercept false. So it took me, so these are kind of things, we all don't read the manual first. We just start doing it. And I couldn't understand why my program didn't give the same result as scikit-learn. It has to be fit intercept equal true, right? No, scikit-learn has the opposite. So this is just in case you want to compare your program. And then there are other kind of the scaling ways. One is called the min-max scaler, which many people also use. So you would have to study your data set and then decide what kind of scaling do you want to. And then there's also something which is called a normalizer, which scales each data point such that the feature vector has a Euclidean length of one. There's something which is called the roboscaler, and it has, I don't remember exactly what it's actually put the text here. I never used it actually. So one of the things which is frequently used is this, which I mentioned. So you have a column vector, and then you simply subtract the mean value, and you divide by the standard deviation if you have it. So if you don't have it, you would put the standard deviation to 1. But you can actually have experimental data where you have the standard deviation. And some of you are probably familiar with the chi-square datum. And the chi-square function is actually a function where you scale the data by dividing by the standard deviation and subtracted away the mean value. Now, this can be useful when we come now to ridge and lasso regression, because then we can actually put an emphasis on data beyond the intercept. So we are not penalized by the intercept, and that tends normally to give a better value for the mean square error, in particularly if you have outliers. So there is an example here where, well, you can actually do that with, if you use pandas. So in this specific case, what we have is a matrix we are setting up, a 10 times 5 matrix. So this is the matrix which we have here. You can calculate the pandas, so you can do this yourself. So you can calculate the mean value easily. So it's just using this function mean, and you have the standard deviation. So you can do a scaling now where you take these pandas, the design matrix minus the mean value for each column, and then you will see now that the column, which you see here now, they have been scaled by taking out the mean value. So that's a pretty common way to scale the data. But it has a consequence that if you keep the intercept column, that will become 0. And if you want to invert your own code, use your own code to invert the matrix, you will have 0 in one column. And that clearly will give you problems when you're looking at matrix inversion. So the min-max scaling, yeah. So let's now just look at an example which we have here. And there's an intercept, an example of an intercept handling. And this was actually an example which Øyvind made. And then we're going to look at some other examples after the break. But perhaps now, before we move on to the code, it's okay to take a small break and just stretch legs. Is that okay? So I'm just going to put the recording on pause. So I mentioned before the break that we are going to look at the comparison between the code which we could write and what a library like scikit-learn would give us. But we have to be a little bit careful. And this applies in particular if we are dealing with a polynomial fitting. If you're not dealing with a polynomial fitting, we don't have this problem with ones along the first column. So just to give you the kind of mathematics, if you go into the lecture notes where we have the Jupyter book, there is a note on rescaling of the data. And what we are doing now is to calculate the derivatives with respect to the different parameters. And if we're looking at the intercept, when we take the derivative of the cost function, which in this case is a mean square error, we are ending up with an expression which runs like this. So we would have the intercept parameter. And then if we now multiply away the constants 2 over n, we just have these sums, and beta 0 is just a constant. So that means that we get n times beta 0. And this quantity which we have here, if we divide that by n, that's just the mean value of y. And so we can actually then just sum up. So we get n times beta 0 is now equal to y of I minus, and in this case, I'm just looking at 2 possible parameters. So I'm just fitting a straight line, beta 0 and beta 1. And then what I get now is just this sum over all the values here, multiplied with beta 1, and I have isolated beta 0. In general, you would have a sum of all the j's as well. But now I'm just specializing to beta 0. There's only 2 parameters, the intercept and the slope. And then you see now, if you do the math, you divide by 1 over n, you can then define the average value for the column vector x1, which is just this quantity here. So that means that you can then rewrite this beta 0 in terms of the mean value of the output, which is something you can calculate immediately. And then the mean value which you have for a specific column. So at the end, you're going to do this in more general terms. You will have it for all the columns here. So it means that the beta 0, if you now leave out the intercept in the fitting, so it means that for the design matrix, you can now take out that column, and you can get the intercept back again by simply taking the mean value of the variables here, and then you have the optimal values for beta, and then you simply take the mean values of each column in the design matrix, and then you can find the intercept. So this is something which is pretty easy to set up, and what's many of these functions in libraries do by default is actually to scale your data in this specific way. It's, if you don't say anything, it's normally done by default. So when you're comparing your own code and you're a little bit in doubt whether your code is functioning or not, there are some small things you need to keep track of. So if we go back to the code then, so let's just look at the Jupyter notebook here. So this is a technicality and it doesn't sound so exciting, but it's something which is worth keeping in mind. So in this specific case, if you now look at the Jupyter notebook for this week, what I'm setting up now is a simple function. I calculate the mean squared error here, as you can see. I'm going to compare with scikit-learn, which is a library which is widely used, and that contains a whole set of modules which are called linear regression, which does the fitting for us. I'm constructing a polynomial of degree 2, and I have some parameters beta here in front of my function. So these are the values I want to reproduce. And I'm simply setting up a polynomial of degree 3, as you can see here. I'm setting up my design matrix. And here, what I'm doing now is simply to include the intercept in the design matrix. So this column here, I'm simply now setting up the design matrix for a polynomial of a specific degree. So the 0, 1 is the intercept. The first one is x to the power 1, and then x to the power of 2. So this is my design matrix. And we can, if we now want to, I can print it here. So let's just do that. So you can see the design matrix. And then I have a function where I now simply do the inversion here. So I calculate the transpose of the matrix. So this is ordinary least squares. So I take the transpose of the matrix and multiply with the matrix, the design matrix. And I calculate something which is called a pseudo inverse. I'm coming back to that. What that actually means when we have discovered the Lasso and ridge regression, and something which is called a singular value decomposition of a matrix. And then I multiply with a transpose. So this sign here means matrix multiplication. I should also say something here. If I replace with that one, what would that give in Python?
A normal, I mean, it's not the dot product. But it's
Are you familiar with something which is called the Hadamard product? Okay, let me just quickly mention that. So let me just switch, because that's an important difference here. So let me just bring up the, if you need to calculate something, you will see that in the literature, something. So sometimes you will see, suppose I have two vectors, V, which now contains the element V0, V1, down to Vn minus 1. And then I have a vector W, which now has W0, W1, down to Wn minus 1. But sometimes you will see a symbol like this. So it's not the tensor product, but it's actually meant as a Hadamard multiplication. So that means that what we are doing now is we're taking element-wise elements, V0 times W0, V1 times W1, etc. So if you do that in Python, what you're doing then is you're simply taking the same elements of a vector multiplied with the other elements. So just keep that in mind, because it's easy when you write the code to just write the standard multiplication sign and just forget that you're dealing with vectors and matrices. So this is just a Python technicality. So when we do the matrix multiplication, we have this sign here, or you can actually just have the matmul function which you can invoke. So I'm just printing out the design matrix, and then I perform the fit by inverting the matrix and just finding the parameter beta. And then I use scikit-learn, which now has a function which is called fit. It takes as input the design matrix, then it takes as input as well the output which you have one. And in this specific case, what I'm saying now is, and this is actually where I went wrong for 2-3 hours, because I put true. So I didn't look up the manual. So it's actually the opposite. So when I want to keep the intercept, I have to write fit intercept equal false. Then what I can do next then, if we go down, I can now take away the intercept column. And if I take away the intercept column, then I'm not including that in the fit. And then I actually don't need to write fit intercept true. You don't need to have it because it does it by default for you. But then when you're comparing, you need them to calculate the intercept explicitly. So what I've done now is I'm calculating the fitted data, as you can see here. So I'm sending in x minus the mean values of each column and y minus the mean value of y. So this is a scale data where I'm subtracting the mean value for each column in the design matrix, and I'm subtracting the mean value from the output. And then I have this formula then where I can actually calculate the intercept, which is now the mean value of this y offset minus the mean value of this x offset times the parameter beta. And if I do that, so let's run the code here. What you will see then, so here you see the design matrix. So this is just the intercept. This is x to the power of 1, and this is x to the power of 2. And that seems to agree, right? The numbers here make sense. And you see now the true beta is this one, the fitted beta. I don't get exactly the same result here, but I'm almost there. And then, because I have some additional noise on everything. And then I have my sklearn fitted data. So you see the parameters here. This is my own code, and this is what scikit-learn gives. I get the same. You see the mean squared error with the intercept column. My own code and the one in scikit-learn, they're just small deviations here. You're just at the level of numerical precision. And then you can calculate the manual intercept when you don't fit it with the intercept. So this is the fitting without the intercept. So this contains our beta 1 and beta 2, and this is beta 1 and beta 2. But one thing you see here is actually that it doesn't change your mean squared error. But this is going to be important when we now move into ridge and lasso regression. Because if you leave it out, you're going to penalize the mean squared error in different ways. So essentially, this is just a way where you do the fitting with and without the intercept and reconstruct it. Now, if you have sine and cosine functions or other types of function and you don't have an intercept, then there is no reason to think in terms of these kind of quantities. It's only if you do a polynomial fit where this problem actually comes up. So I'm just mentioning this because when we now move on to ridge and lasso regression, there are some technicalities which can actually lead to a smaller mean squared error. And we need to understand where the root for that is. So I'm going to skip these kind of codes here, but I wanted to go back a little bit to the type of problems which we can end up with. So I need to say something about the singularity decomposition and also the matrix inversion we are doing. So if you now look at the matrix inversion here, you see now that the root of all evil resides in a matrix which can have a determinant which is 0, or that means it has an inverse which diverges. And clearly then you cannot solve the problem, right? So the if you look at the polynomial fit, or you have sine, cosine, or orthogonal polynomials, or orthogonal functions in each column, then normally you know that the matrix, you have to invert them. Each of the columns will be represented by vectors which are orthogonal to each other. And in that specific case, the matrix inversion, as a consequence of that, the matrix inversion is painless. We most likely won't have problems with matrices which cannot be inverted. However, in many applications, you can have strong dependencies between each column in your design matrix. And you don't know that before. So if you're doing a polynomial fit, you're normally safe. But if you're not doing that, then you have data like the CompSci data, which I mentioned. In the CompSci data case, you can have one feature which is given by the radius, and you can have another feature which is given by the surface of the tumor. And the surface is proportional to the radius. So you may then expect that there will be correlations between the columns in your design matrix. And then you can run into problems with the matrix induction. So then the question is, what do we do? Now, before we move on to these kind of calculations, if you now look at the design matrix, so let me just bring up the whiteboard again. And just ask you a simple question, because this is a cheap trick which you can actually do. So let's bring up the expression for the optimal parameters, beta, which are given by the transpose of x minus 1 x transpose times y. So the problem we face is that if the determinant of this matrix is 0, then we cannot perform the inversion. So we can have the det of xt, which is equal to 0, which means that there's at least one eigenvalue which is 0, and we cannot calculate the inverse. So then we have problems. This leads to problems. So this nice and neat algorithm, we can't use it. Now, if you look at this matrix, X, there's a cheap trick to avoid. This determinant X transpose or the inverse being, or the matrix being non-invertible. What is the simplest possible trick you could think of to avoid a determinant which is 0? And this is actually what motivated ridge regression when it was introduced. So if you have a matrix, let's now just write this matrix X, T, or H, and just call it H, because we're going to later call this the Hessian matrix, which in this case it's proportional with the second derivative of the cost function for ordinary least squares. So this matrix has elements H00, H11, and all the way up to HP minus 1, P minus 1. And then we have H0, 1, and then we have H0P minus 1. And then we have all these other matrix elements here. Actually, there's something very nice with ordinary least squares, which we're also going to need next week. And that this matrix here is proportional with the covariance. I'm coming back to that. So there are many small things which we can bring together in ordinary least squares, which link both to like the second derivative of the cost function, but also something which is called the covariance matrix. And we're going to remind you of what the covariance is, but one step at a time. So if you look at this matrix here, and you fear that the matrix may have a determinant which is 0, how can we avoid that? Simplest possible way. This is actually a cheat which you will see in many old programs.
You can zoom an epsilon.
You can add an epsilon, that's what you meant, right? Some more add, yeah. Along which matrix elements?
Not.
Yeah. The diagonal. So the trick which many people did, suppose you take an epsilon now, and suppose now it's epsilon is put to 10 to the minus 10, right?
You need to have a suspicion of which direction, like, you might just multiply away you might make it a 0.
So you can actually see if you just take a 2 by 2 matrix, you can actually get a determinant which is only 0. So what you would do then is simply to have H00 plus epsilon, H11 plus epsilon, and up to HP minus 1, P minus 1 plus an epsilon. And then I'm just marking with X's all the other matrix elements. And you can convince yourself if you do that with a simple 2x2 matrix, which has a determinant which is 0. So in principle, this means that your H goes over to H plus some lambda with multiplied by the identity matrix. So what it means then is that your parameter beta hat becomes equal to a matrix H. So this is the matrix in the original we wanted to invert. H plus lambda I inverse of X transpose times Y. And this is something which we would rewrite as X transpose times X plus this matrix lambda. And Y has obviously dimensionality P times P has the same dimensionality. Minus 1 of X transpose of Y. So what you see here, and you would actually, if you go back and look into programs which were written in the 50s and 60s and so on, you would often see 0 as a variable being set to a small number. And then you could see something like 0 being added to specific matrix elements. I'm not kidding. This is a cheap trick. Now, the thing which is nice here is that this leads to what's called breach regression. And we can actually argue for this from a statistical point of view, and which makes it pretty nice in terms of a statistical link with standard regression and statistics. We're coming back to that. But what this leads to, this is actually called beta at ridge, or just ridge regression. So let me set up the cost function. So we can derive this equation if I now define a new cost function. So this goes over to C of beta for ridge. And that's equal to the standard mean value or expectation value of the mean square error as we defined earlier. So y of I minus y of I tilde squared. But now we have a new term which goes like a parameter lambda, and then it has a sum over j equals 0 up to p minus 1 of beta j squared. So this introduces a new parameter. And we will also see later that this lambda has to be equal to larger than 0. We'll come back to phi. It should be, when we've done the statistical interpretation, phi should be larger than 0. And it's normally limited, so it shouldn't blow up. So we normally put a limit on this sum over j equals 0 to p minus 1 of beta j squared. This is normally smaller or equal to a number t, which hopefully is not infinitely long. So this parameter becomes a hyperparameter in the theory. And one thing you can show, if you calculate now the mean squared error for these quantities, and actually the mean squared error can become smaller if you use this approximation. So this lambda parameter becomes a parameter we can tune in order to get a better mean squared error. For you to get that. So we can actually, with this one, we have the possibility now to tune this cost function so it actually becomes smaller than the one we would have with the standard ordinary least squares. So if you now take the derivatives with respect to what we had previously, so let's now take a look at it. So we can just rewrite this in a more compact way. So what we have now is 1 over n, and then we have the norm 2 of y minus x times beta And then we get plus lambda times the norm 2 of the vector beta squared. So this is just a compact way of setting it up. And what we can do next now is to optimize this quantity with respect to beta. And what we get then, if we now use the results from last week, we get 2 minus n, we get x transpose times y minus x times beta. But then we have plus 2 times lambda and multiplied with the vector beta. And we want this one to be 0. So what I can do now, when we have these expressions, I multiply away 2 over n. And if I have 2 over n, the only thing which happens is that I get a new parameter lambda times n, which I just call a lambda tilde. And it's just a parameter, and I cannot just call it something new again, right? So if I multiply away now 2 over n, that means that what I get is that I have x times beta times x transpose, and then I get plus, and then I have lambda times n multiplied with beta is equal to y x transpose times y. And then I can always relabel this as a new parameter, lambda tilde. And then if I don't want to keep the tilde, I just call it lambda again, because it's just a parameter, right? So at the end, you see now that the beta, the optimal one, is now going to be given by this matrix x tau, x transpose times x, plus lambda times the identity matrix inverse, multiplied with x transpose times y. So if I define a new cost function which has an additional parameter I can tune, then this additional cost function allows me now to actually invert the matrix without any problems. So this matrix that you see here, this one, this is invertible. Now, what we're going to see later is that the variance of the parameters beta is going to shrink.
Nice.
The mean squared error, or the cost function, will give us a better estimate of the error, not a better estimate of the error, but a smaller value. So we can actually get a smaller mean squared error if we actually use and tune this parameter number. So this becomes our first encounter with hyperparameters. And you're going to see many of them. Actually, many of you are going to be deeply disappointed by machine learning. Because at the end, we are going to tune so many parameters that you're going to ask yourself, what's the point in doing all this? This is just parameter tuning. And I hope I can say, move away this kind of level of disappointment. But there's always a kind of disappointment when you say, oh, we just introduced a new parameter. Now, when we come to the statistical interpretation here, you will see that this way of writing the cost function has an interesting statistical interpretation. So we are going to show later, so I'm just anticipating this, we are going to show later that the output y follows a normal distribution. If we also assume that the parameters beta follow a normal distribution, when we then optimize so that we have a maximum probability, we are then going to get ridge regression. So when we come to this statistical interpretation, you will see a much neater motivation for this parameter lambda. So now just look at this as a way, if you're familiar with something called the Lagrangian formalism, you can always add some additional parameter, a Lagrangian multiplier, and then you have another optimization problem. So this is actually now an optimization problem with a constraint, where we actually put a constraint on the sums of these betas. So this is one way of looking at it. And it gives us a parameter by which we can tune the cost function so that we actually minimize or get a smaller mean square error than we have with ordinary least squares. Sometimes, however, ordinary least squares does the best job. But we don't know that a priori. And if ordinary least squares does the best job, there is no need to invoke complicated methods. Okay. Okay. So let's. So this is actually the derivation of the ridge regression. Let me also state another type of ways you can deal with such hyperparameter, because that gives something which is called Lasso regression. But Lasso regression does not have an analytical expression for the parameter space. So we actually need to solve them numerically. So in Lasso regression, the cost function now contains the mean square error, the standard definition we have seen, y minus x beta. But then the hyperparameter lambda is now multiplied with the norm 1 of the vector. So in this specific case here, we have the beta squared, but there's nothing which hinders you in choosing another numerator. And in that case, what we have is a parameter lambda multiplied with the norm 1 of the vector beta. And let me just quickly remind you of the norm 1 of a vector. This is actually the sum j p minus 1, and then you have the absolute value of beta j. And we know that when we take the derivative, as we discussed last week, of the absolute value, then we get a discontinuity at 0. So just to remind you that if I now take the derivative of d of x with dx, we know that that one is equal to 1 if x is larger than 0, and minus 1 if x is less than 0. Now, many practitioners just put it to 0 at 0, but we have a discontinuity at 0. So this leads to a non-analytical expression. And the general case here is normally something which falls under the convex optimization problems, if you're familiar with that. We are going to wait with these things a little bit. So with Lasso regression, we are not going to get a nice analytical expression for the parameters beta or the expectation value and so on, because we have this discontinuity, which means we have to plug in an if test. If x smaller than or larger than, then we have different expressions which we get. We are going to come back to this. What I want to do now is actually to go back to the interpretation of these methods. So I'm going to do two things now. So one is the mathematical interpretation of these methods compared with ordinary least squares, what they're actually doing. Because this parameter which you see here, this parameter lambda, is also called a shrinkage parameter. So this parameter, as you will see, is going to shrink away some of the parameters which are less important. So it's a way to get rid of degrees of freedom. And we're going to see that explicitly. But before we do that, we need to look at the singular value decomposition. So the singular value decomposition is going to do two things for us. One, we are going to find a way to calculate the inverse, even if the inverse diverges. And two, we are going to use the singular value decomposition to actually prove, one, that the matrix X transpose times X is a convex, leads to a convex problem, but also how we can illustrate the mathematical properties of, let's say, ridge regression compared with ordinary least squares. So we're going to try to catch two birds with just one stone. But let's remind us, so have you heard of the singular value decomposition? So who has never heard of it? Okay. So I'm just going to give you a reminder, and I hope you don't get offended if I go through some of these mathematical properties. So if we have a matrix which can be diagonalized. We know that we can always decompose a matrix. If we don't have a matrix which cannot be diagonalized, that matrix can always, or a matrix which has zero eigenvalues, which is better, or zero determinant, such a matrix can always be decomposed with a singular value decomposition. So any matrix can be singularly value decomposed. So let's try to look at that. To me, that is one of the most beautiful theorems in linear algebra. So the singular value decomposition, if we now look, as we said, if we have a matrix like the one you see here, this is a matrix. When you look closer, suppose this is your design matrix where we have the intercept and then we have some values here. First column is the row-wise sum of the other two columns. That means the rank, or the column rank of a matrix, is a dimension of the space spanned by the column vector. So this, the rank of this matrix X is equal to the number of linearly independent columns. And in this particular case, the matrix does not have rank 3, but rank 2. If you now look at another matrix, if you look at this one, so this is a case which you could take now and just add a parameter epsilon, and you will then find that the determinant is non-zero. But this specific case has a determinant which is exactly equal to 0. So the matrix looks innocuous, but it is actually a singular matrix. And it's equivalent to say that the matrix has at least an eigenvalue which is 0. Now you can fix this singularity, as we said, by just adding this lambda. So that's a cheap trick. And actually, many people did that. And when we discuss reach, that's actually the case. But the singular value decomposition, one of the basic properties of it, is that you can decompose this matrix X. You can always do that. And you can always decompose that in terms of an orthogonal matrix. A matrix now which contains the singular values, and I'm going to define what they are, and then another orthogonal matrix. So, like this matrix which we looked at, this one is not diagonalizable, but even if it is not that, we can always perform a singular value decomposition. It can always be decomposed into such a matrix. So let me just bring back the basic definition of that on the whiteboard. And we are going to use this next week when we meet in order to analyze what the ridge regression and lasso regression are doing for us. So let's just write this down with SVD. This is going to be the last thing we do this week. So any matrix, that's matrix, which I just call for X, can be decomposed as, so we would now have a matrix X in terms of an orthogonal matrix U times this matrix we call sigma and times a matrix V of T. So let's just write down some of the basic properties, and this is where we're going to start next week. So let's assume that this matrix X, as we defined earlier, is an n times p matrix. So n could be equal to p, but just let's leave it like that. This could be our design matrix. And that means that we can have a matrix U, which is an orthogonal matrix. And this matrix U has dimensionality n times n. But these are orthogonal matrices. I guess you're familiar with orthogonal matrix, right? And the matrix V has the same properties. V of T of V. It's also given by the identity matrix. And V is now a matrix of dimensionality P times P. So these are square matrices. And they're orthogonal matrices, which means that the matrix U is something we can write out in terms of the column vectors. So we would have a column vector u0, u1, up to u of n minus 1. So these are the column vectors. So you can take u of I transpose times u of j. These are now the vectors. These are the orthogonality relations. And similarly, the matrix V can be rewritten in terms of the column vectors. So the V0, V1, all the way up to V of P minus 1. And again, I have a V of I transpose times V of J, which is equal to delta of J. So these are just definitions which I'm setting up. Then what I have next is that this matrix sigma is now a matrix of dimensionality n times t. And along the diagonals, you have the so-called singular values. So there's a sigma 0, there's a sigma 1, and they go up to sigma p minus 1. So that would be the rank of this matrix. And then we have 0x. So this reflects the fact that you may have an eigenvalue which is 0. So you cannot escape that. This means again that when I look at this, this is sorted so that sigma 0 is larger than sigma 1, is larger than sigma 2, etc. And it is larger than sigma p minus 1, which is larger than 0. Now, what we're going to do next week is to look at the singular value decomposition of this matrix X and how that can help us in explaining the difference between ordinary least squares and ridge regression. And we are going to see that this parameter lambda in the ridge regression is going to drive to 0 some of the parameters. So we can actually define some effective degrees of freedom. So if you have a matrix, a feature matrix, which contains, let's say, 30 parameters, and you have you're looking at housing prices, and you would expect that the number of rooms is strongly correlated with the price of the house, but you may expect that the color of the chimney is not very much correlated with the price of the house, right? So if you're making a model where you're looking at the price of the house, you could leave out the color of the chimney, right? Unless you have a horrible color. But that you can always paint and get a nice color. So clearly, this will be a feature in your design matrix, which may be totally irrelevant. And then ridge regression is a model by which you can tune away less relevant parameters by adjusting this hyperparameter number. So we are going to use the singular value decomposition to show the differences, but we're also going to use that in order to calculate stable inverses of matrices, even if the matrix has determinants close to 0. So I'm going to stop here now, and I'm going to leave you all in suspension to next time, so you're eager to hear about the singular value decomposition. Is exciting. Let me just stop the recording there.